Hello viewers, today we'll be talking about the working principles and applications of the infrared thermography temperature measurement. An infrared thermometer is a device that measures the infrared radiation, which is a type of electromagnetic radiation below the visible spectrum of light emitted by an object. The most basic design of infrared thermometer consists of a lens to focus the infrared thermal radiation onto a detector, which converts the radiant energy into an electric signal. This configuration facilitates the temperature measurement from a distance without the need for contact with the object to be measured.
There are many types of infrared temperature sensing devices available today, including configurations designed for flexible and portable handheld use, as well as for mounting in a fixed position to serve a specific purpose. The most common types of infrared thermometers include spot infrared thermometers. These devices measure the temperature at a spot on a surface. And second, infrared scanning systems. These devices scan a larger area as the spot thermometer points at a rotating mirror. They are widely used in manufacturing processes involving conveyors or web processes, such as continuous piles of material along a conveyor belt or large sheets of metal or glass exiting an oven. And lastly, we have infrared thermal imaging cameras. These cameras are essentially infrared radiation thermometers used for measuring temperature at many points over a relatively large area to create a two-dimensional image called a thermogram. This technology is more software and hardware intensive compared to the other types of infrared thermometers. Our eyes work by seeing contrast between objects that are illuminated by either the sun or another form of light. How thermal cameras work is by seeing heat energy from objects. All objects, living or not, have heat energy that thermal cameras use to detect an image. This is why thermal cameras can operate at all times, even in complete darkness. Because thermal cameras work by seeing heat rather than reflected light, thermal images look very different from what's seen by a visible camera or the eye. In order to present heat in a format appropriate for human vision, thermal cameras convert the temperature of objects into shades of gray, which are darker or lighter than the background. On a cold day, a person stands out as lighter because they are hotter than the background. On a hot day, a person stands out as darker because they are cooler than the background. Called emissivity is a major factor in the temperature measurements of such devices. Emissivity is defined as the ratio of the intensity of radiation emitted by the surface at a specified wavelength and direction to that emitted by a black body under the same conditions. So, the emissivity of a black body is 1, and the emissivity of all objects range from 0 to 1. Considering this property, there are two main types of bodies. Gray bodies have same emissivity at all wavelengths, and non-gray bodies have emissivity which varies according to the wavelength. This change causes accuracy problems in the temperature measurements. The radiation from an object is sensed by the sensor and it captures the radiation. The sensor is very sensitive as it can even detect a radiation of about 0.0001 watts. The heat energy is converted into electrical energy, which is amplified and modified into output voltage. A central processing unit digitalizes the electrical signal using a 16-bit analog to digital converter, and the arithmetic unit inside the processor calculates the temperature value of the object using Planck's radiation law, which results in a temperature reading on the infrared display. Reasons stated, thermal cameras are good sensors for seeing in the dark because at night, background objects tend to be cooler than a person at 98.6 degrees Fahrenheit. Under ideal conditions, people are well emphasized at night because they appear brighter than the background and stand out even in zero light. However, outdoor conditions are rarely ideal, especially during the day when darker objects absorb the sun's energy and heat up, an effect known as thermal loading. When objects in the scene become uniformly hot in any given area, many cameras have difficulty mapping the narrow range of temperature differences into a useful image. The result is an image with large areas that look whited out or blurred out and undefined. This makes it difficult to see what's happening in the scene, and it makes it difficult for smart thermal cameras to automatically detect objects accurately. The image shown on the slide shows a daylight image from a thermal camera which cannot effectively compensate for whiteout. Details such as the car, the bus, and the cyclist, and the walls become blurred out, and you cannot identify clearly which is which. So now that we understand the working principle, limitations, and advantages of thermography, let's take a look at more specific examples of its use in industrial R&D, academia and research, and the military. In industrial R&D, we often use thermography for electronics inspection. Printed circuit board designs are challenged with the heat dissipation management without sacrificing performance or cost. Accurately understanding heat has been extremely difficult as the size of electronic components have continued to shrink in size. However, thanks to thermography, engineers are able to easily visualize and quantify heat patterns in the devices that they create. Thermal imaging can be used whilst complex PCBs are still at the design stage for the avoidance of subsequent faults and expensive recalls. In the automotive industry invests more in research and development than any other industry with the aim to produce more efficient, safer, and higher performing automobiles. Being able to bring reliable new models faster to the market is one of the key factors of success in the industry. Thermal imaging allows automotive engineers to improve the designs of airbag systems, validate efficiencies of heating and cooling systems, quantify thermal impacts on tire wear, perform quality checks and bonds and welds, and much more. There are extensive use of thermography in academics and research. We will take a look at two of them. The first is life sciences, where thermography is an accurate, quantifiable, non-contact diagnostic device used to visualize and quantify changes in surface temperatures. Applications include vascular evaluation, tissue condition, muscle strain assessment, and bleeding point detection. Furthermore, in fast motion events, high-speed infrared imaging allows microsecond exposure times that stop the apparent motion of dynamic scenes and permit capture frame rates exceeding 10,000 frames per second. Research applications exist in the areas of ballistics, supersonic projectiles, explosives, combustion processes, lasers, and much more. Thermography is also used in the field of non-destructive testing or materials testing. In stress analysis, stress and fatigue testing are common test methods in mechanical engineering and materials science, but provide limited information on complex structures. Thermal stress mapping provides thousands of stress measurements simultaneously, even on geometrically complex components. Compared to strain gauges, this technique provides faster, more complete information to researchers. Historically, we've seen heavy use of thermography in defense and aerospace applications. For example, in tracking, thermal imaging camera systems complement video tracking systems by increasing visibility in low light or unfavorable haze conditions, allowing the tracking system to maintain target contact and constantly update the target's bearing, range, and elevation. In technical surveillance and countermeasures, infrared imaging is used to identify heat signatures from covert surveillance devices. Even devices hidden within objects can be revealed by the minute energy given off in the form of infrared radiation. Clearly, thermography is an incredibly powerful measurement method, and we're seeing increasing use in everyday situations like at the airport, where it's used to screen for H1N1, which results in elevated body temperature due to fever, and even in novelty applications like the analysis of textile fibers. So we thank you for listening to our presentation today and hope you find thermography useful in your future research. Thank you.